if life began on Mars, it probably began around the same time that it began on Earth. So 3.5, 4 billion years ago. But on Earth, sort of kind of paradoxically, it's much harder to look back in time because Earth's active. It's got weather, it's got volcanoes, plate tectonics, all this stuff. So the surface is constantly being renewed. And so it's very, very hard to get samples from Earth of Earth as it was 3.5 to 4 billion years ago. Whereas on Mars, it stopped being geologically active about 3.5 billion years ago. So it's been in deep freeze. And so these river deltas that Perseverance is roving across now are pristine river deltas from 3.5 billion years ago. They're time capsules. So it might be easier to understand the origin of life if it began on Mars. It might be much easier to do so than it is on our own planet.
Welcome to the Pretty Intense Podcast. We're getting into a realm today that is truly one of my favorite realms to talk about. I'm the most fascinated by probably that in psychology. But in fact, we kind of entered into a little bit of those realms because within the realm of physics, and we have Brian Cox on the show today, who's a British rock star physicist. Theory of anything started with an idea. We talked about black holes, consciousness, space and time, fractals, like so many areas of physics and science in the universe that I just love it. And as we learn and understand more and more about our universe, we know our role in it and know how to live our lives. And so that's why I love it so much. But of course, we talked about aliens, extraterrestrials. We talked about the question that he wants answered in his lifetime, which is at the end. And yeah, I think you're just going to love it. This is such a cool conversation. Brian is touring the US and Canada. He has, I think, 50 stops on his tour. I was disappointed to hear he wasn't in Phoenix yet, but he's coming to you. So if you're interested and you're in the States or in Canada, you can find tickets to Brian's shows at briancoxlive.co.uk for any of those spots that you want to go see him. In the meantime, enjoy this episode. If you like this show, if you like the kind of things that I talk about, I would just be so honored if you would follow, if you would subscribe, like it, send it to your friends, and then leave comments and the things that you guys grab onto and really love. And I see the views, then we'll just keep doing more of them. So enjoy the episode. Hi, what time? Are you in England right now?
Yeah, just about to fly to New York tomorrow. And the first show is Washington, D.C. on Friday.
That's so exciting. Where do you live in England?
London.
Oh, nice. I lived in Milton Keynes when I was a teenager, racing.
Oh, yeah. I was going to ask why, but presumably because your family were there.
No. Oh, no. My family didn't go. I left when I was 16 and they did not come with. So I lived there from 16 to 19, pretty much on my own. Racing cars. So did you ever get into racing being in England? Like, did that ever trip your trigger? Or
I've never, the only car I've driven really fast officially was on Top Gear,
Oh, yeah. That's a very popular show.
And I went faster than Bear Grylls, which was...
No, you didn't. Oh my God.
Yeah.
Bear is such a nice guy. I did his show Running Wild. He's a really cool guy as well.
He's great, but he's slower than me in a car.
I'm going to have to give him some crap about that. I'm definitely going to text him and be like, Brian Cox said he went faster in a race car than you. I'm trying to guess, buddy. Why don't you have the bravery? Where's it at? Because he sure does. He had me jumping out of helicopters and rappelling across canyons and all kinds of frightening stuff. But did they have you on the show Top Gear just as a guest to experience cars, or were you like breaking down the physics of cars?
No, it was just it's a thing. It used to be called Star in a reasonably priced car, but it was when they were doing it with rally cars. So it was a bit of a rallying in a Mini, which was quite cool. And so that's what I did. So I was specifically there to race Bear.
That's awesome. Well, then let's step aside from racing because that's not at all what I want to talk about today. Your realm of expertise is so fascinating to me. The amount of time that I walk around in the day and just wonder what's real and what's happening. And then thinking back to when I was a kid and looking up to the sky and thinking to myself, it goes on for infinity. But what is at the end of infinity? Nothing. It doesn't. I can't. Oh, my brain. Is that what you did when you were a kid? Did you look up at the sky and just go, I need to know?
Yeah, I mean that's how I got into science. It was astronomy, just like you, just looking up at the night sky. Something captured my imagination, and fortunately for me, I made the connection. I thought, well, actually, learning about these points of light and what they are is science, and so I started paying attention at school to science because I wanted to know about astronomy and also science fiction. Actually, I grew up, Star Wars was the huge thing when I was 9, 10 years old. And so I connected all that as well and thought it's all the same thing. And I want to know more about it. And that's the wonderful thing about astronomy, as you say, is the more you learn about those points of light in the sky, the more wonderful they become. In the morning at the moment, the planets are up kind of early morning. And Jupiter, for example, if you look at that just through a pair of binoculars or a small telescope, you see the moons. And then you realize that one of those moons, Europa, has an ocean below its surface, which has got more water than all the oceans of the Earth combined.
Is the size of Europa similar to Earth?
It's smaller. It's kind of almost a small planet sized. So it's smaller than the Earth, but it's just water beneath the surface. I was at JPL a few weeks ago, actually, where they build the space probes. And they're building a thing called Europa Clipper now, which is going to go to that moon. And one of the reasons is because it's one of our prime candidates for life. So then the point of light that you're looking at might have life on it or in the ocean, and off you go.
Did that also make you wonder when you looked out to the sky whether or not there were other entities out there too?
Well, yeah. And, microbes might be really common. So we're also, as we speak, there's a rover called Perseverance on Mars, which is now in a river delta. It's just arrived, an ancient river delta. And it's taking samples below the surface because 3.5 billion years ago, that surface was underwater. And so we want to know whether there are signs of life. And the most amazing thing about that mission is that Perseverance, the rover, is the first bit. So it's packaging up samples and it's going to leave them on the surface of Mars. And then the next thing, another mission is going to go and land another lander on Mars, which is going to go and collect the samples, put them in a rocket. And the rocket is going to be, believe it or not, catapulted up off the surface. And then they're going to light the rocket and it's going to fly into orbit around Mars. And then they're going to send another mission, which is going to go and find this thing, which has got the samples in it, which is only about the size of a baseball. And then it's going to find it in orbit around Mars, get it, and then bring it back to Earth. And ultimately, it's going to crash land in Utah in the deserts. And then they're going to go and find that and bring it back to the laboratory to look for signs of life on Mars. It's the most incredible. It's called Mars Sample Return. And the more you talk about it, the more crazy
right. That does sound like quite the choreographed mission because there's so many missions. Now, I've heard you talking about this before and thinking that maybe there's going to be information in those samples, in those core samples, to how life began, and it might help us understand how our life began. Is that accurate?
Yeah. The interesting thing about Mars is that if life began on Mars, it probably began around the same time that it began on Earth. So 3.5, 4 billion years ago. But on Earth, sort of kind of paradoxically, it's much harder to look back in time because Earth's active. It's got weather, it's got volcanoes, plate tectonics, all this stuff. So the surface is constantly being renewed. And so it's very, very hard to get samples from Earth of Earth as it was 3.5 to 4 billion years ago. It's almost impossible. Whereas on Mars, it stopped being geologically active about 3.5 billion years ago. So it's been in deep freeze. And so these river deltas that Perseverance is roving across now are pristine river deltas from 3.5 billion years ago. They're time capsules. So it might be easier to understand the origin of life if it began on Mars. It might be much easier to do so than it is on our own planet.
How far down are those?
The water now is way deeper. But this was surface water 3.5 billion years ago.
Yeah.
So the idea is that if there were microbes in that river delta, then their remains or the traces they've left will be just below the surface. And that's why we're taking these samples to bring back to Earth.
So if we can look back to that time and say, maybe this is an indication of how life started, would it be far-fetched to think that if we just look to how we're doing it right now to find life, that that's just how life started then too? So like extraterrestrials or you're finding another planet to live on. Could it just be someone from another planet coming to figure out and like, oh, look here, this is how it started. Somebody visited and said, this looks like a nice home.
It's one of the big questions we have about the origin of life is, of course, how often did it happen in a solar system like ours? It obviously happened here. Or did it? Because we know that material is transferred between the planets. So we have Martian meteorites on the Earth. We have bits of the Earth on Mars, although we've not found them, but because bits of Mars land on Earth, we assume that bits of Earth land on Mars. And so it's not completely impossible that life began once on Earth or Mars and got transferred. And so the first thing we want to know, if we find signs of life on Mars, is it the same? So does it look, does it have DNA? Is it in some sense the same as the life on Earth, or is it different? So was there a different genesis? How many different ways are there of being alive? We don't know, because we have only one example, which is Earth. So these are profound questions. And then to go on to your next question, then you start saying, well, but what's the chance that given microbes, the origin of life, little cells or something like that, what are the chances of those cells ultimately getting together into things like you and me, which are these hugely complex things, the most complex things we know of anywhere in the universe, the things that can have a conversation, right, and think and feel and bring meaning to the universe in a very real sense. And all we know, again, is that it took about over 3 billion years from the origin of life on Earth to get anything more complex than a single cell. It's about 3 billion years. It's a quarter of the age of the universe. And so what I talk about in the live show actually is if I was to guess, and we don't know, but if I was to guess how many civilizations there are in a galaxy like the Milky Way, with 400 billion suns and countless trillions of planets, I'd guess there might be a handful, maybe even one, which is us. I think the chances of civilizations appearing on planets, it's a big ask when you think about it, isn't it? I mean, to think, it's one thing to have some chemicals getting together and turning into a cell and it's a living thing, and it's a huge deal. It's a big thing in itself. But then the idea that those cells decide to collaborate together and build spaceships is a whole other question.
Right. And create these complex missions to get things off Mars. So then would it be accurate to say that if you thought that there could be a handful or even one civilization in a galaxy, that there would be one to a handful in every galaxy?
The Milky Way is not that atypical that we know of. Our estimate, by the way, for the number of galaxies in the piece of the universe we can see, which is called the observable universe, is 2 trillion. Right? 2 trillion.
That's a lot of neighbors that are not real close.
So I think the Milky Way is fairly typical. We don't really see anything that's massively unusual. So I think that I'm sure, as sure as I can be, that there are civilizations out there somewhere in the universe. But the question really, if we want to ever meet them, or we really want to, see extraterrestrial life, the question is how many are in our neighborhood? And I'm being loose with the word neighborhood because the Milky Way galaxy is 150,000 light years across or something like that, with 400 billion suns. So it's big, but let's say that's our neighborhood. Imagine if we're the only one in there. There's quite a responsibility we have, I would say, if that's the case. I was asked to give the intro, the COP26 climate summit. So it was quite an honor, actually. They said to me, what would you say to the world leaders? If you've got one message to them about the progress we need to make of climate, what would it be? And I said this. I said that as far as I know, it's a possibility at least. So let's say it's our operating premise that we are the only civilization in the Milky Way galaxy at the moment. That means that this planet, this little speck of dust, notwithstanding its physical insignificance, is almost indescribably valuable, because it could be the only place where atoms have got together to think. and feel, and in a very deep sense, bring meaning to the universe. Because I would argue that you need things as complex as human brains. You need thoughts to have meaning. And so if you collectively, world leaders, through inaction or deliberate action, remove us from this world, then you may be responsible for eliminating meaning in a galaxy of 400 billion stars, potentially forever. That's the responsibility that you have. And that's an example of why I think that science is so valuable. It's not because it has the answers to everything. We don't have the answers to everything. Science is fundamentally a humble pursuit. It's based on the idea that we don't know everything. Therefore, we try to find out and do research. But it does give us perspective. My great hero, Carl Sagan, said that astronomy is a humbling and character building experience. So it's humbling because it tells us that we're tiny, it's a speck of dust. But it's character building because it says that we might also be extremely valuable and we might underestimate our cosmic significance. So we have a tremendous responsibility. I think it's a good working assumption. And I don't think that, the more world leaders and our politicians, the more perspective they have, and the more they understand the potential tragedy of damaging this world. I think that I really do think the better they behave. They just need to do a bit of astronomy. In fact, I'd launch them into space. But, people talk about commercial space. Maybe we'll talk about it. But one of the great benefits for me would be to launch every world leader into space before they start, so they can look at the Earth from space and get a sense of its beauty and fragility, and ultimately, I think, its significance. And then, we can choose. Maybe we can vote which ones to bring back. But broadly speaking, I'd bring most of them back again. And just say, there you go. Now you've seen what you are responsible for.
Yeah, I think that's an absolutely fantastic idea. Why is that? Like, what is taking so long? Is it a complicated? Obviously, it's complicated, but from things I've heard, it's like timeline wise, presumably we coulda, shoulda, woulda been off planet by now. Is there anything that holds that back? And I think that, as you just said, talking about world leaders and everybody understanding what is on the line, looking at our planet, like, why are we fighting each other? I feel like there's all kinds of memes and funny things about aliens looking down at Earth going like, they're still fighting each other down there. Like, if we got off planet and if world leaders could see it from that distance, maybe they would say like, wow, we're all for one instead of fighting within. It's kind of like, it's like viruses within a planet just sort of like fighting each other.
Yeah, it sounds almost, when you say it, and I say exactly what you just said, and it almost sounds naive in a way. People say, oh, you've been so naive. But actually, if you look at the astronauts, and I've been so lucky to meet a few astronauts, and they all say that many of them, the Apollo astronauts were test pilots, they're military people. And so they weren't particularly disposed to these kind of contemplative thoughts when they left the Earth. But all of them say that. They all say that. There's one, I can't remember, it's one of the Apollo astronauts. He was asked, what do you think when you went around the moon and saw Earthrise? And he said, why the hell can't we get along? It vividly sort of comes into view when you see the Earth for what it is, which is a tremendously valuable and yet fragile place. And so I think it would make a difference. And the answer to your question is we can do it now. So the real leap forward has been really, I think, the private sector now. It's SpaceX and Blue Origin developing reusable rockets, which makes it really cheap, in the scheme of things. I talked to, I'll name drop now, but I spoke to Jeff Bezos. It was great fun actually talking to him, and he pointed out that imagine that transatlantic flights. I'm going to fly to New York tomorrow from London. Imagine that you got on the plane in London, flew to New York, everyone got off the plane, and then you destroyed the plane, right? Imagine how much the ticket would be. But that's what we've done. All our space exploration up until very recently was single-use rockets. And now we don't do that anymore. Then I think that space is going to become more accessible to everybody. And hopefully, therefore, it should be a responsibility, shouldn't it? I think, the next president of the United States, he could be flown, or she could be flown into space for a fraction, way less than $1 million, right? You could fly them up, let them look at the Earth, fly them back again. I think that would be a great investment.
I definitely agree. How come we haven't been to the moon in like 50 years? And how come I've seen videos that says we lost the technology to go to the moon? What is the truth about all that?
We sort of initially lost it after the 1970s.
What does that mean? What does it mean to lose the technology?
It's very, very difficult and expensive to build a Saturn V. In those days, in the 60s, I'd say it was right on the edge of our capabilities. It's astonishing that we managed to do it.
They say now that your telephone has more capabilities than what they had in totality to fly to the moon.
Way more. So it was almost too hard. And I remember I got to speak to Charlie Duke, who walked on the moon, Apollo 16, and he said that his dad remembered the Wright brothers flight. Right, so his dad remembered the Wright brothers and then saw his son walk on the moon. So that's just almost impossible to believe. It was done. The other thing Charlie Duke said is that he said when you've got like 700,000 engineers and unlimited budget, you can do a lot, right? What they had, right? So that's how they did it. But then, of course, at the time, it was very difficult, very dangerous, and very expensive. And it was one of the great human achievements that we managed to do it. Now it's a lot less dangerous, a lot cheaper, and we have the technology and the computing power, as you say, to do it rather much more easily. So that's why we're going back now, because you don't need 700,000 engineers and unlimited budget. You now can do it. SpaceX are pretty close to being able to do that in the private sector.
Just a Delta flight. Now it's just a Delta flight. Where do you want to go? Oh, let's go to the moon.
It won't be long. I don't think it'll be long until people, initially people with quite a lot of money, but then the price will come down. That ordinary people, if they really want to, you sometimes go on a vacation and you say, right, I'm going to save up for 10 years and for my retirement or whatever, I'm going to go on this amazing vacation. I think people are going to be able to hop up on the suborbital flights and see the Earth from space at that kind of level within about 10 years, I would guess.
So now you're saying suborbital, that's not the moon though. That is within orbit, Earth's orbit, but not all the way to the moon?
Yeah. The little hops that Blue Origin do now and Virgin Galactic have been doing, those things. And then SpaceX, obviously going to orbit, it's much more difficult. Going to the moon is still difficult, but it's nowhere near as difficult as it was when we had, as you said, this thing that was like not one of the phones we have now, but like a Nokia, one of the old things.
Right. Oh, I had one.
It's like that, right? I mean, it's that computing power at best.
Yeah, that's crazy. What about what do you say? What do you think about, or what is your counter to the conspiracy that we haven't been to the moon and the Van Allen radiation belt and all the things? Like, what is someone like you say to that?
It's total shit. it's just nonsense. But it's nonsense at the same level. There's lots of nonsense in the world. There's flat earth people and all sorts of stuff. And so ultimately it is interesting why there's a serious side to it. It's not so serious, I suppose, if people don't believe that they went to the moon or whatever it is, or think the Earth is flat. The problem is that what you're seeing there is a distrust of science and a distrust actually of our political system. I mean, the idea that for 50 years or more, the political system can hide one of this great expenditure and hundreds of thousands of people's experience and hide it from everybody. I mean, that's nonsense in itself if you think about it. I mean, they can't hide. You go back to the scandals that affected past presidents and things like that. I mean, they can't. You can't hide anything, right? I mean, in our country now, we've got a prime minister who couldn't hide the fact that he had a party during COVID lockdown. So how these people are competent enough to cover up the expenditure of hundreds of billions of dollars over 10 years and keep hundreds of thousands of people quiet when they can't even keep a drinks party quiet is beyond me. The really important point, though, is if it goes back to why is it important for people to have a basic kind of understanding of science? It's not because you need to know the things, how far the moon is away, how many galaxies there are in the observable universe. It doesn't matter whether people know that. But science is the way that we acquire reliable knowledge about nature. So it's the way we answer questions which are good questions, such as if we carry on burning fossil fuels, then will there be an impact on the climate? Right? That's just a completely sensible question to ask.
Sure.
And the way that we answer those questions, and we found out that there will be an impact, and there is being an impact, is by doing science. That's important. So the conspiracy theory can appear harmless, but then you get conspiracy theories about pandemic response or climate change or so on. Those are important problems because we live in democracies. And so if you have enough people who really don't understand how we acquire reliable knowledge, how to weigh or how to seek out trusted voices in society who know what they're talking about, and then make decisions based on that knowledge, then we have a real problem in our democracies. We're liable to do really silly things. So it becomes serious when it becomes about existential threats that we face, rather than just some people thinking that you can't fly through a Van Allen belt, which is, I should say that you can go. The thing is, you can read the research that was done. It's a good question. It's like, will launching a human being through into sort of beyond the protective cocoon of our magnetic field and out into space, will they be able to survive the radiation dose? And it is dangerous. And astronauts do get higher than average radiation doses, and they have to be careful. And you can't launch them when the sun's very active. And actually, you have to launch them carefully so you can avoid the worst of the radiation that's in things like the Van Allen belts. But you can actually read all the research that was done, so you can see how it was done. And then the question becomes, well, why don't you just read, do a bit of reading?
Because they're fun concepts, and people people kind of read reaffirming things, right? It takes a disciplined, open mind to be able to say, okay, if this is this, we have this perspective, now let me look at the opposite perspective and evaluate all of it, so I can make my own decision or make an educated decision. And I think probably for scientists and physicists and cosmologists and everyone in the science field that is figuring out new theories of things and equations, is that you guys live in that space of being proving things right and wrong, right? Everything that comes out gets highly scrutinized, and that's just part of the process.
It's one of the most important things. When we do science at school, right? So people go to school and do science experiments and things. What are they really learning? They're not really learning about how a pendulum swings or whatever it is. What they're really learning about is that process of acquiring knowledge. Richard Feynman's one of my great heroes, Nobel Prize-winning physicist. And he wrote a brilliant essay, which you can get online. You just type it in, Richard Feynman. It's called The Value of Science. And he wrote it in the mid-1950s. It was a speech he gave, actually. And he was saying, what's the most valuable thing that science gives us? And it's not, the knowledge or even mobile phones or weather forecasting or healthcare, all those things, really important things. But ultimately, what it is humility. It's that he called science, he defined it as a satisfactory philosophy of ignorance, which is a beautiful definition. And it's the idea that he said it's the idea that we approach doubt and uncertainty not with fear, right? We don't approach doubt with fear. We approach it with excitement and wonder. That not knowing, admitting that you don't know, is the first step on the road to wisdom. And Feynman, by the way, wrote that, and he was very concerned about this propensity that we have as human beings to think that we know everything. We get it all the time. You turn on the TV and you go to a political chat show, whatever it is, and you get people who think they know, right? They give every impression of thinking they know how to run a society. Running a society is difficult. As Feynman said in this essay, that what a democracy is the acceptance that we don't know how to do it. So you change it every 4 years. You've got to understand that you've got to accept the fact that you don't know everything in order to be a democrat. If you're not a democrat, you're not someone who celebrates democracy. I don't mean democrat politically, right? I mean someone who supports democracy. You're not that if you think that you know how to do everything and you're so sure. And the way we've acquired all this knowledge that I'm going to talk about in my shows about the size of the universe, the age of the universe. How do we measure these things? How do we know this stuff? How do we build spacecraft that go to different planets? We did it because there are some people who accept the fact that they don't know everything. And so they're very careful and they try to find out. And that's the important thing about science and science education. It's teaching people to be humble and be comfortable with uncertainty. And then you can move on and you can acquire reliable knowledge about the world.
Is there something that has been proven to be different than your original opinion in your life that's really big?
All the time.
When name of the game, I forget. But is there something that is central and something that felt very true to you that you had to change your mind about based on information?
Actually, well, recently, I'll give you a physics example in a minute, but in just the way that I look at society. So in the UK, we had this big boat, right? And we left the European Union, all right? And it's like, I think that's a disaster. I think it was a bad choice. And for a while, I thought it was such a bad choice that I thought, oh, we can't do this, right? It's just a terrible mistake. But then I came to understand what I've just said. I mean, I've always, the thing about democracy, right? I've always known that. I've read Feynman for years. But I thought, actually, the fact that decisions in your country swing against you. So the fact that sometimes there are people doing things that you think are just completely, the wrong thing to do. And you don't agree with the government at all. You don't agree with what's happened. And then sometimes you agree and things go your way. The fact that that pendulum swings is the sign that we live in a free society. Like the moment that your government, even if they're doing everything you want, and that pendulum is not moving against you, then you should be really worried, because you should think, well, this means that we no longer live in a society where things are being debated and where different opinions and different points of view are being celebrated and allowed to flourish, because the majority go one way and the majority go the other.
Right.
The moment that stops and the moment you agree with everything is the moment you should get very worried, because you're living in a dictatorship then. You're not living in a free society anymore. So I realized in thinking about a case where I really fundamentally disagreed with the decision that people made, I realized that actually I should celebrate that, unfortunate as I think it is and as disastrous as I think it is, because it tells me that I live in a free society, and the pendulum will swing back if we make the arguments. So that's a political version. The science one I'll give you is it's an interesting story. The thing I'm researching at the moment, and a big part of my live shows actually will be talking about black holes, and that's because black holes are the most baffling and interesting things, and I could talk about them forever. But one of the questions that was asked initially by Stephen Hawking, actually, by work he did back in the 70s, was what happens to stuff that falls in? Does the information, if you throw a book into a black hole, is the information gone from the universe forever? He discovered that black holes, and this really was what Stephen Hawking is most famous for in physics. He discovered that black holes evaporate away over time. It's called Hawking radiation. And so one day they're gone. So the question is the information gone? Right. And for many years, Stephen thought that the information was destroyed in black holes. And then he changed his mind. And now the current view is that no, the information comes out. And we're pretty sure now, almost completely sure, that information survives that process of going into a black hole, gets radiated out into the universe, and in some sense, it's never lost. But there's one of the great physicists of the 20th century and 21st century, Stephen Hawking, changing his mind because he got a deeper understanding and more work was done. And that's what science is all about.
Yeah. Thank you. Those are great stories. And especially from someone brilliant like yourself and explaining how you change your mind, and someone like Stephen Hawking. Okay, well, then let's talk about black holes, because I find it fascinating as well. Maybe we'll back up and start with energy, just the universal understanding. And maybe I think this is accurate. Correct me if I'm wrong. That energy can't be destroyed. It's only transformed. Yep. So everything is energy. Right? So even if a book went in there, it's some form of energy. Is this correct?
Yeah.
With that in mind, then transformed, what could it become? Like, what could the things that fall into the black hole become? Presumably, it doesn't always have to come out as a book, right? If we're just using that example.
Well, no. So if you think about something like a book, and then if we wind back, how does physics work as we understand it at the fundamental level? It says that if you know everything about something, let's say a book, and then let's say we burn the book, so we set it on fire, then physics says that if we could collect everything, all the gas and all the ashes and everything, and measure everything that came off from that fire perfectly, which is very hard to do, but if we could do it, then we could run back time and reconstruct the book.
Okay.
So given that we know everything about something or with a great deal of precision at some moment, we can predict what it's going to do in the future and what it was doing in the past. That's called determinism. Okay. Well, that's central to science. It's how we look at the universe today and we model it and run it back in time and forwards in time, and we see the Big Bang and we can measure the time back and all those things. So the question with black holes is that still true? So if we could collect everything that comes off the black hole when it's evaporated away through this process called Hawking radiation, and it's just particles, nothing left, the black hole's gone. Could some omnipotent being, right, in the far future with a huge quantum computer feed everything in and then reconstruct everything that fell in? And the laws of nature, as we understand them at the basic level, say yes. But the laws of nature also said, as we understood them at the basic level, with the black hole, initially they said no. So we had a fundamental clash with our laws of nature contradicting themselves, right? Essentially, that was the wonderful thing about black holes. And it turns out that now it seems that ultimately, as the black hole evaporates away, the information that fell in gets imprinted into the radiation that comes off the black hole, which is a really tremendously bizarre thing to happen. And it's really what it's done is it's challenged us to reassess our understanding of space and time. And now the consensus view, I think, from the black hole research is that space and time are not fundamental things, that they emerge from something deeper. Einstein had this wonderful phrase, something deeply hidden. He said, when you look at nature in detail, you can catch a glimpse of something deeply hidden, which is the deep structure of nature. And it seems that there is such a structure of space and time. And that deep structure, which is what we call quantum theory, preserves information. So the patterns evolve and change over time, but the patterns are always there. And you can always, if you could collect them and you were smart enough, you could run it back and see the patterns in the past.
So one of the most fascinating things within science to me is fractals. Like, I just think fractals is fascinating. I constantly look at the way things are and just wonder what level, like what part of the fractal loop we're in. Is our universe is it fractal in nature?
I think at a deep level, it isn't. So fractal, there's a great thing. If you go online, you can look at the Mandelbrot set, which is this mathematical structure, ultimately, And you can zone in. When I was little, actually, so I'm being really geeky now, I wrote a computer program to draw one. It's a really simple thing. And in this really simple bit of mathematics is this infinitely complex structure. And as you zoom in and in and in, you see the structure again and the structure again and the structure again. So I really recommend you go online and look at Mandelbrot's set and spend an afternoon or an evening zooming in and exploring this bizarre land that's mathematical. So you can go infinitely deep, basically, and carry on, and you just see pattern after pattern after pattern repeating itself. The universe, what black holes have told us is that the universe isn't like that. There's a really weird, strange results from black hole physics. And it's that, so let's say I say to you, how much information in bits, right? So literally in bits of information, like the memory in your phone, how much can I put in some given region of space? So you could look at the region of space in front of you now, just look in front of your nose, look at a little cubic centimeter or something of space, whatever it is, and say, how much information could I fit in there? The answer is that the maximum amount of information you can fit is you keep putting bits in, and ultimately the thing collapses into a black hole, right? So there's kind of a limit before you make a black hole and the whole thing collapses. And the amount of information in any given region of space seems to be proportional, or actually equal in some sense, to its surface area and not its volume. So that's like saying, if I was to ask you how many books can you put in a library, how much information can you fit in a library? You'd say, well, it's got to do with how many books I can fit in. It's to do with the volume of the room. How many books can I get in the room? That's it. Or how many hard disks or whatever it is. But it turns out at a fundamental level, nature seems to say, no, it's only about the surface. It's not about the inside at all. And so this is leading us to think that we vastly overestimated the amount of information you can store in any given region of space. And this leads to something called the holographic principle that we could talk about, which is that's
I love that principle. I read the holographic universe book and I thought it was fantastic.
So a hologram is the basic level. It's a piece of film, right? So a flat thing, like a sheet of paper, two-dimensional thing, with all the information on it necessary to make a three-dimensional image of a thing. And it seems that at a very deep level, the universe is like that. And people are even, it came from black hole research, but people are even now, although it's not fully understood by any means, beginning to say, well, okay, so that means that there's an equivalent description of us. So me and you and everyone that's listening and watching, there's an equivalent description, which is in some sense, and physicists always use that phrase, by the way, when they're waving their hands around, right? In some sense, right? So it means we don't fully get that, right? We don't fully understand it. But in some sense, the information, our thoughts and everything that we experience is equally well represented on a surface surrounding us. So it's almost, and in that sense, you could say that we're holograms, and that's called the holographic principle. And that's really bizarre, but it's coming from research in black holes.
What part of the black hole? Is that all the information's on the outside?
Well, so the problem with a black hole is that from the outside, the thing behaves in a certain way, and that's how we view it, right? So we're out, we right. See one. There's a galaxy called M87, for example, about 55 million light years away, and we have a photograph of the black hole in that galaxy, and it's a huge black hole, 6 billion times the mass of the sun, supermassive black hole. So we know these things exist. We've got a picture of one in that galaxy. So from the outside, they're weird, right? So if I'd said to you, you go into the journey into the black hole, and I watched you go in, so I sat from afar and watched you fall in, I would never see you cross into the black hole. You would freeze on what's called the event horizon, and it's actually from some perspectives, I could imagine that you actually were completely incinerated on the event horizon, and all your ashes came out into space, and I could collect them and I could reconstruct you, right? If I was clever enough.
Humpty Dumpty.
So I could do that. But from your perspective, you would fall in across the horizon inside to the black hole. You go into the interior of the black hole. you could float around in there in the interior of the M87 black hole for, I think it's about 35 hours or something, if I remember rightly, before you meet the end of time. So you go to the end of time ultimately in the black hole. So from your perspective, you go in and you end your days at the end of time, which is called the singularity in the black hole. Whereas from the external perspective, you never cross the horizon.
So you're saying if you watched it, I wouldn't change, but so what goes in? My consciousness,
No, you would go in. There's a thing called the equivalence principle in relativity, fundamental to Einstein's theory, which says that you wouldn't notice. So you could fall in across the horizon of the black hole into the interior, and you would notice nothing. You'd sit there looking at your watch, it would tick at 1 second per second. You would feel no ill effects at all. In you go. But from the external perspective, you never get in. So the modern understanding is that both are true. So our universe is constructed in a very strange way, where things that you might think are a contradiction, actually, it just depends on your point of view, whether you got in or not. But the outcome, it ultimately is the same. So no contradictions appear. And that's been central to black hole research. It's got a fancy name. It's called black hole complementarity. And it's broadly speaking thought to be correct now. But it challenges us to think about what we mean by reality, because it means that our reality is so strange, so much stranger than we could possibly have imagined. Still works. The laws of nature apply, but it's not quite what we expected. Our common sense is not a good guide.
How strange do you think it is? How far can your mind go?
Everybody's mind. I mean, this is the wonderful thing about science. It's not. I always, when I go into schools sometimes, and people have a tendency to think, well, scientists are just really clever.
Well, you are clever. I mean, you are clever.
Scientists are not any cleverer than anybody else, right? They're just people that spent their time learning about stuff like this. They're no cleverer than someone who's a great musician or a football player or whatever it is, a great sports person. That it's all about practice and about the thing that captures your imagination. And I think, to be a good guitarist, you have to practice as long as you have to practice to be a good physicist, pretty much. You just practice in different things.
I'm curious about space and time and density and dimensions and all of that. And along with that, I'm curious about how general relativity and quantum mechanics aren't always in sync. So maybe explaining what quantum mechanics and general relativity are and where they don't jive, and then going into space and time. And I'm just curious, maybe it's a local phenomenon at a certain density or at a certain dimensional level, but isn't something that crosses over into every aspect of the universe. So what comes to mind when I say all these things?
Yeah, no, they're really exactly the right questions to ask. And general relativity is it's a 100-year-old theory. It was published in 1915. And it's a theory of gravity, which is ultimately, it takes space and time, or woven together into, it's often called the fabric of the universe, right? It's called space-time. But essentially the picture is that anything, matter, energy, warps and distorts the fabric. Mm-hmm. And the thing that we feel as gravity is the distortion of the fabric. And so often you see people, imagining it by rolling a kind of a little ball around on a rubber sheet that's deformed in some way, like a mattress. And the ball will be deflected. And that's basically what Einstein's theory of gravity is. Right. And quantum mechanics, quantum theory is essentially the old-fashioned way to think about it, I suppose. It's our theory of everything else. So it's a theory of particles and forces, how they interact. It's odd. It doesn't. Again, it's the same age of general relativity. It was being formulated around the same time, about 100 years ago, and it doesn't really fit with our intuition. But there are phenomena like entanglement, which is a really inherently quantum thing, and a way you can think about that is to imagine a coin that you can toss, right, heads or tails. And And so then imagine two coins, and I could separate them, and I could toss one of them, that would be heads, and that would be tails, and so on. But there's an idea, if you had a quantum coin, you can set these things up, these two coins, such that they're in what's called a state where I'll say what it is, it's heads, tails plus tails, heads, for example. So that says that if I separate these coins, if I take them and separate them to a light year or across the universe in principle, and I toss one, and I don't know about the other one, so it'd come up 50% heads and 50% tails, and I wouldn't know any different. And the same with the one that I took to the other end of the universe. But actually what you'd find, if you could look at both the results of both of those coin tosses, you would find they never both come up heads or both come up tails, ever. So that's what's called an entangled system. And it's unique to quantum mechanics. It's not weird in a sense. We use it in quantum computers. So it's an everyday feature of the world, but it's not a feature that we're familiar with. So quantum mechanics is an odd theory, but it's very well understood, and it underpins modern electronics and lasers and all sorts of things. So it works. But you're right to say that the great clash that Stephen Hawking really precipitated in thinking about black holes was a clash between a quantum mechanical description of the black hole and a purely gravitational description. And ultimately, it's been resolved, I think, in favor of quantum theory. So there are one or two physicists. There are a few physicists wouldn't agree with that, but I think the consensus is that quantum theory is the base thing, and actually entanglement. So that thing I described about this kind of strange link between the quantum coins, entanglement, we're now strongly suspecting builds up space and time. So space and time themselves are emerging from quantum entanglement. So I think that we're in the early stages of understanding how that happens, and it's really new research, but that's really where we are. So I think I would be safe to say, and I think most physicists would agree, that the base level of the universe is quantum, and all this space and time and gravity stuff really are coming out of the quantum theory.
So you're saying that the penny, or whatever the coin is, has at one side of the universe, it's a heads, and the other side of the universe, it's a tails, and it always correlates?
Yeah. So it's a
polarity? Is it sort of does that even matter? Is polarity part of that, of like, the universe trying to balance itself?
No, it's the fact that you can have a description, just in our normal world, we have a description of these of things that are completely separate from each other. So the coins would be, you could correlate them by saying, I will give you a little box which has two coins in, and I'll always set them up so one's heads and one's tails, or something like that. The key thing about entanglement is that the system is set up so that you don't know. You can know everything about the system. So it is, in quantum language, heads, tails plus tails, heads. That's what it is. That's a complete 100% description of that system.
Mm-hmm.
But if I separate out the bits, I know nothing about the two bits of the thing at all.
Mm-hmm.
Right? They're completely correlated. All the information about the system is distributed across the whole thing. None of it's in the individual parts.
Mm-hmm.
So you look at an individual part, it'll be completely random, heads, tails, 50% of the time. But the whole thing is set up in such a way that if you set it up and take these coins away, if that one's going to be tails, this one's going to be heads. They were neither before those measurements were made, before the coins were tossed. They weren't secretly heads or secretly tails. So it's a completely different logic. It's a different logical structure. So it's very counterintuitive. But we're talking about polarity. There's a property of particles called spin, where this is realized. So they're like quantum coins, really. And we use it now in quantum cryptography, for example. So this is becoming technology now, this idea of using entanglement. And also in quantum computing, extremely exciting. So we're now, this is not just wishy-washy wild stuff. It's fundamental. We use it in laboratories as it's people think of entanglement as an information resource now, a
Mm-hmm.
resource that we can use to build computers.
Mm-hmm.
But it's profound because it really does seem to be the case that entanglement builds up space-time. So it's almost like it's the underpinning structure. I mean, imagine a world where at the fundamental level, space, which is this thing we take for granted, it's the room that we're in. We talk about things being 1 mile apart or something. We think we know what we mean by distance and separation.
Yeah.
Actually, no, underpinning that, it does seem, is a world of quantum entanglement in which there is no concept of distance or separation or space. It emerges. It's like saying, you talk about us, right? You, right? What are you? You're a human being, and you're thinking and feeling, and we're having this conversation. But actually, there's another level, which you could call a deeper level, where you're just atoms. So you're just protons and neutrons and electrons, and the protons and neutrons are made of quarks, and they're all stuck together. And that's a description of you.
I mean, that's true.
And that's true. It is true.
Right?
But it isn't you. It feels like it isn't all there is to you, right? There's also you, a human being with thoughts and feelings, and the most wonderful structure in the universe, which is what human beings are. In the same way, we're saying that that space and time are like that, and it's as incomprehensible, but then again, no less incomprehensible. Right? It's the fact that a human being can be made of atoms. What we're saying is space and time can be made of something else, which seems to be quantum entanglement.
And that's what Einstein said, spooky things happening at a distance, right?
Einstein really didn't like it. Yeah. So he called entanglement spooky action at a distance. He didn't think the world behaved like that. And really never, I mean, he understood very well quantum mechanics. It's a myth that he understood the theory. He was one of the instigators of it. So he understood it perfectly well. He just didn't like it. Right? He thought that really it's not going to be the base description. There's going to be something else. Actually, that now in the 21st century, we think, no, there isn't anything else. That's really it. That is the way the world behaves at a deep level. And the things that we're really familiar with actually just emerge from this deeper level.
Do you think we're getting closer to a theory of everything?
Yeah, I really do, actually. I mean, you've got to describe what that is. I mean, it doesn't mean that we know everything, right? But
is there an equation that explains how things happen in every way at every level, at least at this point in time?
I mean, I should go back. When I said yes, I'm going to now say don't know, right? But what I'm going to say is that our study of black holes is pushing us, and this is really papers, and I talk about these in the live show. I think it's really wonderful because I'm talking about research that's been done now. So papers that have been published in 2021, 2022. This work is revealing a deeper level of description of reality. Whether it's the base level, we have no idea. I mean, it could be you carry on. What's that saying? It's turtles all the way down, right? Who knows? Who knows where the Tower of Turtles ends?
I don't know anything about turtles, but
it could be. It could be that we're certainly getting a glimpse of a deeper description of reality. I think that's fair to say. Now, whether that is a theory of everything, whether it's the base level theory, I really don't think anybody knows. And it's almost not worth speculating because it's kind of meaningless, probably. All we can do is keep digging. And the wonderful thing about this work that Einstein, set in motion with general relativity and quantum mechanics, and then people like Stephen Hawking and Roger Penrose took that on in the 1970s. And now there are great physicists in the, working now, young physicists. Netta Engelhardt is one, and Jeff Pennington. This list of names, people in their 20s mainly, who are uncovering a deeper description that's beginning to bring these ideas together. So it's great to see this progress that's being made. It's very, very exciting at the moment, and it's moving so fast.
It needs to be talked about, I guess, especially based on not understanding, and this whole idea of being connected through the quantum field. But like, where does consciousness fit into all that? And, I don't know if that's something that you specifically study or if that's just something that you think about. And is there, what are your thoughts on consciousness, and how could that play a role in this connectedness? And when you talk about us as humans being protons, electrons, neutrons, and energy, like, what makes us think and have feelings and thoughts? And is that consciousness, and is that the thing connected to everything?
I really don't think so, and I think that we don't understand what consciousness is. It's called a hard problem. The people who work in this area, neuroscientists, call it the hard problem. We're miles away.
I mean, I interviewed Neil deGrasse Tyson, and he said when there's a lot of books being written about something, we don't get it.
Yeah, it's probably human brains are the most complex things we know of anywhere in the universe. They're harder to understand in very many ways than the universe itself.
Mm-hmm.
Right? Understanding the evolution of galaxies is kind of easy compared to understanding human brains. So we just don't know about consciousness. What I would say, it's a physical property of the universe. It emerges in accord with the laws of nature. As I've said, we know basic laws of nature. I don't think you're going to need to understand quantum gravity to understand consciousness. I think we do very well with biochemistry, and the structure of the brain, I think, will be understood. It's what we call room temperature physics and chemistry and biology, right? So the stuff that happens in the familiar surroundings in which we live. I think that's where an understanding of consciousness will come from. I don't think you're going to need to go to quantum gravity to understand consciousness. So I don't think entanglement and those things, they're a part of the physical structure of the brain, right? So when you can argue that if you want to go down to drill down into deep chemistry, you need to understand quantum mechanics and the way the electrons are in atoms and so on. But I think ultimately consciousness is going to be something that's understood by thinking about atoms and molecules, although we are miles away from understanding it.
What about dark energy and dark matter? Is that just code for we don't get it? Because,
well, the dark matter, so we should say what they are first. So when we look out, we've got loads of evidence that if you look into the way that galaxies interact with each other, the way they rotate, the way they formed in the early universe, we've got huge amounts of evidence that there's more matter out there than we see shining in the sky or in interstellar gas and dust and so on. And it's pretty strong evidence that that's some kind of subatomic particle that we've not yet discovered, but we see it through its gravitational influence. And that we have wonderful models of all sorts of things, many different observations, and they all point in that direction. And to be honest, I think many of us thought that at the Large Hadron Collider at CERN, we'd have seen some evidence for these dark matter particles. We'd be making them in particle collisions, and we haven't done. And that's a surprise. So we're still looking, and that machine has been upgraded, and we're looking. And so we might do, but I think it's one of those things. It's science. Nature is always perplexing and surprising and outsmarts us all the time. So we haven't found yet what that particle might be. So it's still open that there's something else going on, but we're pretty sure. Dark energy is a different thing. It's we are again pretty sure that the universe is accelerating in its expansion now, and that was a tremendous discovery that was made in the 1990s. And Einstein's theory, the venerable theory of general relativity, tells us that if we see how the universe is expanding and changing and stretching, so the fabric of the universe is stretching, it allows us to discern what's in it, the kind of stuff, how much matter and dark matter. And we find that we need some other stuff called dark energy, which is allowed in the theory. So Einstein knew about it. He had one model for it called the cosmological constant that he put in the theory. So it's there. But we really don't understand at a deep level what it is. It's one of the great mysteries. And maybe, we're to speculate, maybe we're going to need the understanding of space and time that we're getting from black hole research in order to make more progress in understanding the nature of dark energy. Maybe. So it's exciting. We're talking about the frontier. But the observation is that the universe is expanding and it's accelerating in its expansion. And that's what dark energy is. So a catch-all term for whatever's doing that, which is a pretty good observation of the universe that we have.
So is there a possibility that there's a correlation between quantum entanglement and this? Because it is assuming that there's some kind of energy needed for that. There's some kind of communication of some sort. And since we don't understand what it is it possible that that's part of that fabric or that?
Yep, absolutely. So it's a great question. And yes, I think that if we're beginning to see that, as I said, many physicists, not all, would agree with this, what I'm going to say. So we're beginning to see that space emerges from quantum entanglement. And dark energy, this accelerating expansion of the universe, is something to do with space. It's some property of space. So it's not, we're a long way off, but it's a reasonable kind of guess that it may be that we need to understand more about the nature of space itself in order to understand what dark energy is. Doesn't have to be. There are theories that have it as some kind of new field that permeates the universe and so on. But it does seem to be something to do with space itself. So there is something fundamental in there that we don't understand at the moment.
Yeah. Are you ever afraid that us as humans are just maybe not supposed to get it? Like we don't have the capability of quantifying, understanding the reality of the universe?
Well, we all we can do is say that we haven't come up to that barrier yet. I mean, there's a great physicist here, a friend of mine, Martin Rees, Lord Rees. He was the Astronomer Royal. Isn't that a great thing? The Astronomer Royal, right? And he's made that point that it's possible that we're just not smart enough. So when we talk about a theory of everything, it may be there is one, but it's just beyond our capabilities. But we have no evidence that we've not reached the limit yet. And I think we thought we might. We were confused about black holes for a long time. And I think many scientists, even 10 years, even 5 years ago, would think, oh, well, this is something for the far future. And then suddenly in the last few years, a few really clever people buildings literally standing on the shoulders of giants, as Newton said, have actually made a breakthrough and found a way of making really rapid progress. So all I can say is that usually, as of now, we've been smart enough, which is a remarkable thing.
I always wonder if we're just zeros and ones. Are we a simulation?
Well, there's two, those don't follow from each other. So are we just zeros and ones? John Wheeler, one of my great heroes, one of the great physicists, the greatest of the 20th century, had this idea. He used to talk about it from bit. So he used to say that information theory, right, the theory that computing theory, ones and zeros, or qubits, which are the quantum versions of that, would underlie reality in some way. And that's in the message that the black hole physics is giving to us. We've got to this realization through thinking about information conservation, how information is shared in systems, how it comes out of systems, like black holes and Hawking radiation and so on. So there is some a good case to be made that thinking in terms of bits of information theory it allows us a very much more powerful window onto nature. So whether that is telling you that the universe is made of bits at a fundamental level, maybe. But I don't think you can extrapolate from that to say that we live in a simulation. It might just be that the base level of reality is best understood and described in terms of bits of information. I think it's a huge leap for which we have no evidence at all to say, therefore, we live in a big quantum computer. I think that's the correct thing to say is it's interesting that many of the ideas from quantum computing are turning out to be useful in describing physical reality. That's clearly true, right? but to go the extra mile and say, therefore, we live inside a big computer seems to me to be a grotesque,
Well, it would be sad.
overextension.
The reality of that would be sad, but it kind of doesn't even change anything.
Yeah.
The truth of the reality, and it helps you maybe understand what's possible or what's not possible. But I find it fascinating how people can fall into patterns and archetypes, and there are certain disorders or cancers or anything, and they have a pattern. There can be two people that have no idea what they have going on, but they develop the same pattern of something, whether it's a personality disorder or a disease. And I just find that kind of fascinating.
Yeah. Patterns. I mean, that's what we do. That's what we search for in nature. That's how you do science, really. You're looking for patterns. And that there's a wonderful book by Johannes Kepler. So Kepler was around in the 1620s, right? So before
Kepler
Newton.
or Kepler?
Kepler. And he wrote a book called The Six-Cornered Snowflake, which is one of my favorite books. It's a brilliant book.
Okay.
And he's talking about walking across a bridge in Prague, and a snowflake lands on his arm, and he looks at it, and he starts thinking about this thing, that the snowflakes, they're all the same, but they're all different. So what is it telling us? And in 1620, Kepler starts thinking, well, it must be telling us about the underlying structure. There's something in there, that it's something deeply hidden. And of course, he's right. It's the water molecule that's doing it, but he could not know that. He didn't know about atoms or molecules. But it's wonderful. And at the end, he says, there's this wonderful, the translation of it I have says that I'm knocking on the doors of chemistry, it says, but I must leave it. I must leave this to you, dear reader, right, to the future, because I can't go any further. I don't know enough. But knocking on the doors of chemistry. And I love that book. It's so wonderful. It's such a beautiful, Kepler was a genius. There's no doubt when you read that book, he's funny and he's insightful, and he was a modern mind at the level of the best physicists that we have working today. But in this world where he didn't know very much, but he's still asking the right questions. He's saying, does the pattern in the snowflake, what is it? The six-cornered pattern thing, what is it telling me about the deep structure of nature? And it's wonderful.
It makes me think of cymatics and thinking about how, you've seen the sand on the drum and they can play it and it shapes different patterns, and how this pattern can repeat in nature, and how, this pattern emerges in different forms at different levels in different ways, whether it's an animal or music, and you wonder what that significance is. Yeah,
and absolutely. And it's about asking that question. It's about what the regularities I see in nature, the shape of a snowflake, the swirls of the galaxies, the way that black holes behave. What are those patterns telling me about the underlying structure? And that's what science is.
What is the most important or most critical question that you hope can be answered in your lifetime?
I would love to know whether we're alone in this neighborhood. So I'd love to know whether there's life on Mars, whether there's life in our solar system, whether there's life nearby. I'll never know. You never know. If the answer's negative, we'll never know, because we can't survey the entire universe. But it would be lovely to see that there are other microbes, and we're searching for that on Mars now. So it's not beyond the realms of possibility. And the other one is to see how the black hole research develops, because ultimately that's our window onto the origin of the universe, if indeed the universe had an origin. So we don't have the theoretical tools yet to talk about really what happened. Did the universe have an origin in time or not? We really in the dark. We don't really know. We know there's a big bang, but we don't know if there's things before that or what the universe was like before that. So I think that's what we need. That's where we need what you refer to as a theory of everything, quantum gravity. And those theories are closer, I think, than everybody thought 5 years ago.
Well, I'll ask you the same question I asked Neil. I'm like, do you think that we're maybe looking for the wrong thing? We're looking for us, but we fit perfectly into this environment, which is so fragile, as you said.
Well, it's possible. I mean, that's one of the reasons we're bringing the samples back from Mars, actually, because it's so difficult to know what to look for when you're looking for living things. But when you're looking for civilizations, possibly again, I mean, people make the argument that maybe there are machines from other civilizations around, and maybe they're too small. Maybe, if they were really smart and their space probes were the size of iPhones, would we notice? Right? The answer is probably not.
Nanobots or whatever.
Exactly. So you're right. We all we can say is that in the limited time we've had, and we've looked and we've seen no evidence of anything. But you're right. I mean, it could just be because things are really small and we just don't see them.
Right. Or it's in the dark energy and it's in a different dimension and it's information as opposed to matter like this, or what we call matter.
Argument that we have a pretty deep understanding of the universe, and if you want to look for different forms of matter, different forces of nature, it has to be quite subtle, because we're pretty good at exploring the universe in some detail. But the science, as I said, is about understanding that you don't know everything. So we certainly don't know everything.
Such a humble place to come from. You're starting your tour of the US and Canada, right? How many stops are you making?
Oh, it's about 50 or something like that. It's a huge tour. So we start.
Are you coming to Arizona?
I'm not coming to Arizona, sadly, yet. So no, and I love Arizona.
We have so much extraterrestrial activity here in our skies.
I'm so surprised we're not, because Tucson is one of my favorite cities, and I was quite disappointed that at the moment we don't have a show there. But we've got shows across, all down into Texas and all across the Northeast, and then all down the West Coast, Midwest, and Canada as well. So we start on I don't know when the podcast going out. We start on Friday, so that would be, what would that be, the 20? What is it? 20 something? I don't even know. See, I'm a physicist, so I don't know what.
You're a numbers guy. Come on, Brian.
Yeah. 22nd in Washington and DC, and then on from there. And it's about 3 months in total. We don't finish until amazing. July.
You're a rock star.
Well, I think the era of stadium cosmology is upon us.
I love it. I very much love it. And if you are coming anywhere within the Arizona region, I would love to come and see your lecture and all of your examples on the screen. I'm sure you have that. Didn't you have a huge show that had like giant screens at some point?
Well, we're bringing them to the US. So it's all LED screens. In the UK, where we have 15,000 people come to the shows, so we have these huge screens, are 100 feet wide, and we just put as much as we can into every theater. So we'll be in very near you, in Texas, and then places like that, Denver, Salt Lake City. We'll put as much screen as we can in there, and the graphics have been developed, for arenas, and so therefore, in a theater, you get a different experience, and you get an experience you couldn't have had no one could afford to do that in theaters, but because we also have the arenas in the UK and Australia, and some big shows in Canada, then we can spend the money on the graphics. We use the graphics code from Interstellar, for example, to simulate black holes. We've used the Unreal Engine, which is the video game engine, to build virtual worlds that actually are rendered in real time in the theater. So we can have sunsets, and the lighting rig interacts with the screen. All these things, this really wonderful technology that we can use. And we're bringing it all to the US, but you get to see it in a more intimate setting.
I would love that. And then at some point you can use like the holographic principles of some sort and create like the sky above us in an arena, right? You could do it at stadiums and just put your maps in the sky.
Yeah, it's a plan. And we've got a classical music version, because there's some classical music in the show. So we're going to, in 2023, we're going to bring the show out and hopefully to the US and Canada with orchestras, and do the same thing in a slightly different show with a symphony orchestra. So we've got big plans.
You're going to create a little vortex when you do that. Love it. I don't even know what that means, but it sounds cool.
I'll take it.
Yeah.
I'll take it.
All right. Well, thank you so much, Brian. This is fascinating, and I could talk your ear off, but I got to go. They said I got to go. Good luck on the tour, and I hope I see you along the way.
Well, so we'll find out. I'll find out where the nearest show is, and you must come. I'd love to see you. So, let's. I will send you a message of where the nearest one is, and
Awesome.
send a car.
Send a car.
I'll send a car for you.
Well, I'll drive it. You send the car, and I'll drive it.
Okay, we'll do that.
Thanks everybody for listening to the Pretty Intense podcast today. I hope you enjoyed it. If you like what you heard today and you want to hear more, please click on the subscribe button.